Good morning, good evening, hello to everyone joining us. Thank you for tuning in. Now I'm delighted to introduce Susanne Doerfler, based in my hometown of Dresden. Susanne is working as the team leader for the battery and electrochemistry department at the Fraunhofer IWS, and she will introduce new anode concepts for solid-state batteries today. Susanne, with that, over to you.
Thank you very much indeed for this lovely introduction. In the next couple of minutes and slides, I'm going to talk about new anode concept for solid-state batteries. So when I talk about solid-state batteries, I mean sulfidic-based solid electrolytes, not polymer electrolyte, just as a kind of definition. And so thiophosphates are actually or have been discussed as very promising candidates in order to be employed into solid state batteries because they are ductile and they have a rather high ionic conductivity. And on the left hand side, we can see a scheme how such a solid state lithium ion battery could look like. So we have, of course, an NMC cathode laminated on a current collector with conductive additive, and we have a current collector on the anode side, and as an active material on the anode side, we actually need to employ a thin film high volumetric capacity anode, because otherwise we don't gain so much into watt hours per liter if we just swap. So if we just use lithium ion battery with a graphitic anode, and if we just swap the liquid electrolyte by a solid electrolyte, then we don't gain in watt hours per liter, and we actually lose in watt hours per kg. And very important is actually the interface engineering between the NMC material and the solid electrolyte, and also the separator layer is also a crucial point. And of course, interface engineering on the anode side, we just heard the talk, the last talk, is also quite crucial. So actually, what are the issues? So especially on the lithium, so when we employ lithium as an anode, then we actually need to struggle with the interface, as I mentioned, especially the cycling rate and also the reversibility of the electrochemical mechanism is limited. So we actually have failure mechanisms that include, for instance, such voids, because we have a solid electrolyte that cannot diffuse into cavities. So it's a quite rigid solid electrolyte. So, and if voids emerge, then we cannot really fill them with a liquid electrolyte. And of course, lithium has the very unpleasant property of being stripped and plated as dendrites or as mossy lithium. And also dendrites can grow along the grain boundaries of solid electrolyte particles. So it's an intrinsic issue, and it's quite, so it's tough to solve it. And also we have decomposition. So especially when we employ thiophosphates with lithium, then a solid electrolyte interface is also built. So what are the solutions? And I think the most promising solution and very prominent solution was given by Samsung SRJ. And they actually employed, or they solved this problem by employing a carbon black matrix with some silver nanoparticle sprinkles. And this layer and this scaffold somehow enables a better plating and stripping mechanism of the lithium. And they showed a pouch cell comprising 900 watt hours per liter and also 1000 cycles. However, this system can be only cycled at elevated temperatures, and also high stack pressure is needed, which is of course detrimental when we think about OEMs that want to implement those batteries into the cars, and then you need to always apply the stack pressure. However, it's a quite promising so-called zero excess anode concept. So the lithium just solely comes from the NMC and is plated into this framework, as I just mentioned. And so at Fraunhofer IWS, we have been working on different anode systems for many years, especially first